the mean and the standard deviation of rolling 24 three-sided dice. And the secret is you do it for an individual dice, and then there's a nice way to scale up from 1 dice to 24 dice. So this is really what we were doing last class with n equals 24. You got to find the mean and the variance of one single dice, and then you involve 24 here to get the general answer for the sum of 24 of them. So what is the mean of a single 6-sided dice, 3-sided dice? Mean of single dice roll. And this is one thing that's hard about math, is if you just say mean, you're going to forget, do you mean the mean of the sum or the mean of an individual one? That's why I like to say a single dice roll, that's the expected value of, let's call it x, where x is this little 3-sided dice. What could x be? It could either be 1 or 2 or 3, and the probabilities are a third, a third, a third. 1/3, 1/3, 1/3. So this is the kind of table we saw before. There was a question like this on the midterm. Please calculate the expected value. In this situation, you can use the simple formula 1/3 times 1 plus 1/3 times 2 plus 1/3 times 3. 1 plus 2 plus 3 divided by 3 is 2. You can also see that 2 is right in the middle of the distribution, right? So there's sort of an equal amount of pulling away from 2. A third of the time, it's a little bit less than 2. A third of the time, it's a little bit more than 2. On average, it's exactly 2. Okay, that was the mean. The mean, I think, is the easier one. Let me now see how many people got it right in the question. So this is your chance. Make sure you put in unanswer here so you get the mark for coming to class today. And let's see what you guys said. How many people got the mean? Reveal what people said. Everyone said 48, and I said the answer was 2. So only 11 people got it right, apparently. No, of course, the answer is 48. So don't forget, I did exactly what I said you should not do, which is I mixed up the mean of the sum with the mean of the individual dice. So the mean of a single dice roll is 2. What is the mean of 24 dice? Mean of the sum of 24 dice, or the average of the sum of 24 dice. That one is the expected value of some big sequence of x1 plus x2 plus ... plus x24, adding up 24 of these. And you shouldn't sweat. You should not try to compute what is these things and the probabilities. You should just use linearity of expectation. This is 24 times that 2, which is indeed 48. So if you said 48, you got it right. Congratulations. And you even beat me. I think I would have said 2 because I forgot what the question said. So great work, everyone who said 48. Fantastic job. The real exciting thing is the standard deviation. This one is a lot harder, but still not so hard. If you know what you're doing, it's pretty quick. Let me see if anybody got this one right. What is the standard deviation? 13 people said they don't know. The most common answer after that was 4. Let's see, any other common answers? After that, it was pretty split. Some other things. The correct answer is indeed 4. So it's 48 and 4. So if you got that right, congratulations. If you didn't, let's do it together. So the thing from last class is that the standard deviation of the sum, the SD of the sum of 24 dice, that will be square root of 24 times the SD of 1 dice. So just like the mean gets blown up by a factor of 24, the standard deviation also gets blown up, but this time by a factor of square root of 24. So not a full 24, but the square root of 24. But how are we going to calculate the standard deviation of 1 dice? Well, what we're going to do is we're going to do of 1 dice, that is the square root of the variance of 1 dice, of the variance of x. And again, x is our little thing here. It's either 1 or 2 or 3. And those all happen with probability a third, a third, a third, a third. How are we going to calculate the variance? You have your choice of formula. You could either use the expected value of x squared minus the expected value of x all squared, or you could do the expected value of x minus the mean of x all squared and do the expected value of that. These are both equivalent. These are both equal to the variance. These are formulas we saw before. And if you do it, you can do either formula. They will both work. They will both give the same answer. One is maybe easier than the other. Let's write down what they are. I'm going to show you this way. I think this way is a little sneakier, but is a little bit nicer. And that's because we already calculated that this is 2. So the expected value of x equals 2. So what does the random variable x minus the expected value of x? What does this thing look like? Well, if x is either 1 or 2 or 3, what is x minus 2? It's either -1 or 0 or 1. So the random variable x minus 2, x minus its expected value, is either -1 or 0 or +1. And these all happen with probability a third, a third, a third, a third. So this is my way of calculating this. If you told me please do this problem in the fewest number of steps that you can, I would subtract 2 from this random variable. By subtracting 2 from the x values, that's what it means. The probabilities stay the same. And now I gotta square this guy up and calculate the average value. So this is this expected value, x minus its expected value. If I want to do it squared, then it's going to be either -1 squared or 0 squared or +1 squared. So this will be the expected value of x minus its expected value all squared. And these are the 3 possible things that happen, either -1 squared or 0 squared or 1 squared. And you add them up and multiply by the probabilities. So a third, a third, a third. And these two are both 1. This one's 0. This is 2/3. So that is how I did it. And the final answer is 2/3. You could also do it directly from this quantity, and you would get 1 squared plus 2 squared plus 3 squared, something like that. So if you do it this way, you will get 1 squared plus 2 squared plus 3 squared divided by 3 minus 2 squared over there. And then you got to do some simplifying to also get to 2/3. Did anybody do it this way? Of the people who got it right? Did everybody do it this way? Put your hand up if you did this way. Okay, yeah. I think this way is a little bit faster because you get to skip the step where you do simplifying this fraction, and you can kind of think of it. It's either 1 above the mean or -1 to the mean, and then when you square it, they both give a contribution of 1.
A lot of 1's nice when the expected value of x is a nice number.
Yes. Well, even if it's not, you can kind of always think about the expected value is somewhere in the middle of the distribution of x, and you should sort of have some negative values and some positive values. When you're calculating the variance, you square them all up and add them all together. If you have only positive values or something in this calculation, you've done something wrong because the expected value is supposed to be somewhere in the middle. So sort of you're supposed to have an equal amount of mass balanced out to the left and to the right. And in this picture, it fits perfectly well. Okay, so that's 2/3. That's the variance. And if the variance is 2/3, then the standard deviation of one dice is the square root of the variance, which is the square root of 2/3. One time when I was in grade 10, I lost a mark because of this. And then I was scarred for life, and now I will never do it again. So we have to fix this. You see, I was never taking a mark off for spelling things wrong, which is why my spelling is terrible. Okay, square root of 2/3. Okay, that's the standard deviation of one dice, and so the answer is square root of 2/3. Wait, I said the answer was 4. Oh no, I've done the same thing again. We want the standard deviation of the sum, not the standard deviation of one dice. The standard deviation of one dice is indeed square root of 2/3, but for 24 dice, let's go back up to where I had it. It's 24 with a square root times this thing. So it's 24 times the square root of 2/3 in a square root. And if you simplify this one out, I cooked it up so the numbers would be nice. 8 times square root of 2. So the 3's cancel. 3 with 24 gives 8. And then you have 8 times 2 is 16. And the square root of 16 is 4. So the standard deviation of these 24 dice are 4. The mean is 48. And once you calculate the mean and the standard deviation, you can do all sorts of calculations with the normal approximation. Maybe I'll do a quick one like that in a second, but any questions or comments about how we got 48 and 4? This is a great bread and butter question for these normal approximations, where the next step is to say, now use the table to estimate a probability here. I'll do that in 1 second. All right, let's do sort of here's a kind of an example problem that you might get. An example. You roll the 24 dice. What is the probability? The probability. The sum is less than 52. Less than 52. So you roll 24, same problem. 24 three-sided dice. 24 three-sided dice. The sum of those dice, the sum. What is the probability it's less than 52? And because we know the mean and the variance, we know the sum S. The mean is 48, and the standard deviation of the sum S is 4. We can do a normal approximation and say that S is approximately a normal with mean 48 and standard deviation 4. And so this question, what is the probability it's less than 52, is one of those questions of you have a normal random variable with mean 48 and standard deviation 4. What is the probability it's less than 52? So you would say, please do the probability that S is less than 52. And the way we do these is we kind of normalize them. So we say that's the same as the chance that S minus 48 minus the mean divided by 4. So I've done some operations on S to subtract the mean and divide by sigma. This is the x minus mu divided by sigma transform. And I did that on the left-hand side. On the right-hand side, I got 52 minus 48 also divided by 4. Right? So far I've done nothing. I've done the same operation to the left and the right-hand side. This thing equals this thing. They're exactly the same. But now is the whole shebang is that this guy is approximately a standard normal, a z value. And 52 minus 48 divided by 4 also works out to something nice. That works out to 1.0. So by normalizing it, minus 48 divided by 4, it turns into the probability that z is less than 1.0. And if you're being really careful, you would do a little continuity correction and worry about, are you including 52 or not including 52? But I'm not going to do that. I'm just going to leave it like this. And maybe my little approximately equal will be slightly less good than somebody else's approximately equal. But in the limit, it's all the same. Okay. And then this one you look up on your table. So you get your table out. And in the table, you look up, okay, we need a z value of 1. And so we look up over here a z value of 1. Where am I on the table? Oh, things are very bright. Z value of 1.0, 84.13% is the answer. So this is approximately 84.13%. So that is a nice problem with dice, solved sort of from start to finish. Once you know the mean and the standard deviation, which you can compute in the sort of simple ways we did before and combine it by blowing it up by the right factors of n, it turns into a normal approximation problem, and you can answer all sorts of fun questions like this. This is incredibly useful in all sorts of fields when you have large averages of things, which happens when you have a big sample of different things. You average them, and you ask questions like this. All right. Questions or comments about that one? Okay. Let's do one more quick question, and this one is a true or a false. It is a true or a false. And this is about the law of large numbers that I told you about last class. So here's the story. Prof. Niga has rolled the three-sided dice 10 times, and the running average of the first 10 rolls was only 1.4. So we were told that the average is 2.0. The average of the dice is 2, but I only got 1.4 in my first 10 rolls. So I'm sort of running badly. I got unlucky. This is well below the average of 2.0 that was supposed to come up. But then he remembers something, the law of large numbers. And it says that the long run average of the dice is getting closer and closer to the theoretical average, 2.0, as the number of rolls goes to infinity. So this was one of the last things we said at the very end of last class. And this statement is definitely true. So this thing in quotes is a 100% true statement. And the reason I'm bringing this up is because the next statement is a true or a false. So the next statement, you got to decide if it's true or false. And here's the statement. That means if I keep rolling, it must be more likely that the dice come up with larger rolls. So maybe to compensate for my first bad rolls, it's more likely that I'll roll a 3 now. And it goes up. That has to compensate the poor first roll. So because I got unlucky in the first ones, it means I must get lucky in the remaining rolls so that the long run average will be 2. Is this a true statement or a false statement? And there's a little Desmos thing we're going to do, but I want you to think of what to do. And very fitting for the last true false of the question, I set it to select all that apply. Of course, only one of them applies. So you have to decide, do you buy this explanation or not? Is it true or is it false? Okay, I'll let you guys think for a minute, and then I will take it up. Okay, 10 seconds left. Get in your answers. Do you think I am due for some good luck later on or not? That's essentially what you are answering. And I'm very curious what people said. So this line of reasoning has a very famous name called the gambler's fallacy. The gambler's fallacy. I guess maybe that name gives you a hint if it's true or false. Let's see what people said. 39 out of 44 people said it is false. And that is absolutely the correct answer. So this line of thinking is called the gambler's fallacy, which is to say that if you get unlucky now, that means you're more likely to get lucky in the future. And sort of people use this law of large numbers to justify it. They say, like, the only way the law of large numbers could be true is if the bad luck balances the good luck. So if we're unlucky now, that must mean we have good luck coming up in the future. And unfortunately, it's false. So it's not true. I made a little Desmos simulation here of the dice to show you what's going on. And so here are my dice. Let me zoom out a bit to make my thing on the right a bit smaller. So this is, on the x-axis, I have the number of dice rolled. I have this nice little table with the values of the dice. So they came up 1, then 3, then 1, then 2, then 1, then 1. And these little blue lines are the running average of the dice. So the very first one, when x equals 1, is just the value of the first dice roll, which is 1. And then when x equals 2, then something starts beeping at me. Let's turn off the when x equals 2. When x equals 2, the running average jumps to 2. So the second dice roll was 3, the running average was 2. And you can see here, I was a little bit unlucky in the first 10 dice rolls. So my first 10 dice rolls, my average was a little bit below 2. But if you kind of look into the future and you see what's happening, is that just over time, it's not that I'm more likely to roll 3s or anything, just over time, the importance of these first 10 dice rolls gets washed away as you roll more and more dice. So if you kind of look, and you look way long into the future, if you look at the first 100 dice, then actually this is the first 10 dice plus a 100 sample of new dice rolls. And that 100 samples is 10 times more important than the first 10 dice. And you can increase this, you can increase the number of dice. Let me increase the number of dice. Dice rolls. Let's make n. Let's make it 200. Let's keep going into the future. And the further you go into the future, the more you see that we're getting closer and closer to that 2. And it's not because the first few dice are getting canceled out by good or bad luck. They're just getting washed away in the limit. So that's how you should think about this law of large numbers thing. And going back to this original thing, I've also drawn what we have calculated. These green areas, these are the envelope of the 1 standard deviation and 2 standard deviation regions. So there's a 68% chance that it should be in this dark region and a 95% chance it should be in this light green region. And we can see what happens when you re-roll the dice over and over again. So I have that over here at the top. So here it's re-rolling them over and over again. These are sort of different ways it could have happened. And you can see there's a lot of variability in the first 10 dice, but no matter what happens in the first 10, it's going to be washed away by the rest of the stuff. So the sort of the first 10 dice, they do not have a big long run effect. Another way you can see that, let me make another slider here. Let's make a W. And I'm going to make the first 10 dice only depend on the W. So here's the first 10 dice. So I'm only going to randomize the first 10 dice now and leave the rest as they are. So only the first 10 dice will get re-randomized. All the rest of the dice here are exactly the same. So here I'm re-rolling the first 10 dice over and over again, and the rest of the dice are the same. And you can see that no matter what happens in the first 10 dice, it might move things up or down a little bit, but the long run average is sort of smooshed towards the mean too, no matter what you do. The long run average does not care about the first 10 dice. Here's another even more dramatic way to see this picture, is I could rig the first 10 dice. Let me be a sneaky little cheater over here, and let me rig the first 10 dice. So what I've done is I've rigged the first 10 dice to be really bad. So the first 10 dice suck. And so this envelope, it's actually, these dice are mean 0 for the first 10 dice. So I've rigged them, they're very bad, but as soon as you turn on the regular dice, over time, you still will revert back to that mean of 2. Some people call this a reversion to the mean. So even if something bad happens in the beginning, it's not that you're more lucky after that. Even if you're just the regular amount of lucky, you will slowly forget about the bad stuff that happened because it's a small fraction of your history. So here it is, reversion to the mean, shown with these envelopes. And all of this stuff, like the areas, are things that you can calculate with the tools we've shown you. It's exactly just a fancy version of the first problem we did. All right. Any questions or comments about that? Seems like you guys all know not to go to the casino, so that's a good win for us. Okay, in the last 20 minutes of the course, we're going to give you a little preview of the kind of fun things you do in stats classes, looking at something called Simpsons paradox. So Gary's going to show you that. Let's see if we can get this set up and going the right way.
Going the right way. Cool.
The microphone.
Microphone.
I have it. I forgot to turn it on. Okay.
Okay. Okay. Let's just gotta get this to play, just like slideshow. And if we post that. That's good. So let me just make lots of noise here for a while. Couple things just before I get going on what we're going to do next. The normal table, we didn't put that up on CourseLink, did we? So I'll put that up on CourseLink, okay? And it's going to be something you need on the exam. We will have some normal questions on there. And but you don't need to put that in your crib sheets because we will supply that table just the same way you got it in class, okay? Furthermore, we are going to be putting up some practice problems. Got to work on them this weekend. How quickly will they come up? I'm certainly hoping they'll be up on Monday at the latest. That's probably a good day that they'll come up with Monday, and then we'll get the solutions up as quickly as possible after that. So you got some reasonable time to get some practice. The other thing about the practice problems, we're going to include some difficult questions in there on the grounds that getting prepared for difficult questions kind of helps get you prepared for regular questions. And I think you can pretty well count on the fact that we will have a couple of, probably a couple difficult questions on the final exam, which will end up getting treated as bonus questions, okay? So you have the capability of increasing your grade more than you can calculate just based on what the final exam is worth, okay? So, but of course to get the bonus you got to be able to do it, and they won't be identified which are bonus questions. It's just things that everybody's capable of doing. That's what we want, is that everybody's capable of doing it, but you got to get the brain wrapped around the right way. So, I think that's what we got to say. And one more thing before I get onto this problem. We brought the originals of test 2, and for those who had their names on their crib sheets, we've got their crib sheets attached to the test, so we can give you their original test 2, probably easier to read than the scanned copy. So we got those. Okay, okay, so we're ready to roll. Now, we're going to take some consensus here, and somebody's got to calculate numbers for me. Okay, so you got to go like get your calculator out, get your computer out, you know, maybe an advanced software like R in order to be able to take fractions. And here's the idea. There's a table, it's got 2 hats on it. There's a black hat and there's a red hat, and the black hat's got 5 reds and 6 blues in it. And 5 red balls, 6 blue balls. The white hat's got 3 red and 4 blue balls. Now, which hat should you pick if you want the highest probability of getting a red ball? Okay, work that out. So you got to be able to, you know, use a calculator to take fractions.
I got my fancy R program here called the Calculator app.
Oh, wow.
Can you see it? Oh, there it is. Okay.
Okay.
5
So
divided
give us like 30 seconds to work it out.
Ooh, okay.
30 seconds. Well, some of you are probably taking fractions in your head. Did you take the fraction in your head? Kind of. You already know which one? Okay, so let's. Mihai, what did we get for that one?
I got 0.83333333 for the first one, and then my calculator stopped.
Okay, how about just give it to me to 3 decimal places, please?
I believe you say 0.83 repeating, of course, is how is how you phrase it.
0.83?
Yeah, 5 over 6. Oh! Oh my god. I did it all wrong. This is so embarrassing. Okay, hold on. So you got to do 5 divided by, and then you don't divide by 6, you divide by 5 plus 6, see? See? Never do any math in your head. Always the calculator. No, this is a terrible idea. Okay, 0.4545.
0.4545. Okay, we can live with that if you round it off properly. And what was our probability of getting a red on this one?
All right, I got 3 divided by 3 plus 4 is 0.42857.
0.4287. Okay, so which one's going to give you the higher probability? Which hat are you going to pick? Well, we're going to just see if people are awake here. I'm going to look for somebody who's looking asleep. How many people are looking asleep right now? I'm going to catch somebody who's like right out of it.
On the last day of the term, trying to take a nap.
You'd go with the black hat. Everybody go with the black hat? Anybody want to argue? Argue? Okay, no? Go with the black hat. Okay.
I'm going to go with the white hat because I'm feeling lucky.
Oh, you're such a silly fellow. What a superstitious guy. Okay, so let's take the black hat. Okay, let's go to another table.
Question 2.
Yeah. So, table 2, we've got a black hat and a white hat, and they've got the balls, and let's see what we get here. So which hat should we take? Now, Mihai, we are going to require your... Oh, this one's actually one I can do in my head. That's pretty rare.
0.666666667.
66667.
All right.
And which one we're going to do with this one? The probability of a red is...
Ooh, this one's only 0.643, let's say. We'll round it off like a reason.
429. 429. We said we're going 4 decimal places.
Ooh, okay.
4 decimal places. Okay, which hat are we going to take? Which hat are we going to take? You're going to take a hat. You're going to take a hat. What hat are you taking?
The black one?
Definitely black. You're not feeling superstitious? Well, okay. I'm glad that Mihai is the only one who's who's making silly decisions.
If you live
like
in
that.
Canada, you have to wear a white hat so you can sneak up on people in the snow.
Okay.
It's like the obvious.
Okay. So we're going to take the black hat. Okay. Okay, what's next for us? What we're going to do is pour the balls in the two black hats together into a black hat. You know, pour one, say, from table 2 into table 1 and, for the black hat, and the same with the white hats. We're going to combine the black hats and combine the balls in the white hat. Okay, so there it is. We've got all the black balls that we had in the two hats. Two black hats combined into a single black hat. All the ones in the two white hats combined into a single white hat. Now, which hat gives the higher probability of selecting a red ball?
Gary, did you know there's a fun name for this operation? It is called the baseball sum. Have you heard this?
Yes, that's a good
Baseball.
one. Yes, and it shows up with Derek Jeter and David Justice.
Yeah, so because in baseball, if you got 5 out of 11, and then you got 6 out of 9, what was your average? It was 5 plus 6, so you add the numerators, and then you add the denominators. So you get 5 plus 6 out of 11 plus 9. And that'll be in the black hat. If you combine these two original black hats, that's the chance for the black hat over here. Right? So it's the baseball sum of the previous two things.
Okay.
This is also how students do fractions before we tell them the right way to do it.
Yeah.
Okay. Well, let's go.
Okay, we're going to combine those.
Baseball
Combine
sum.
them. Okay, so we got the black hat. Now we've got them combined. Black hat. White hat.
Okay, here's the black hat. I got 5 plus 6 divided by 11 plus 9, and it was 0.55. So that's the combined black hat. All
11
right?
out of 20, eh?
Yeah, 0.55.
Yeah, it's about, about 0.55555?
No, just 5.5, and then you stop. It's amazing. It's a real
oh, exactly, 11 out of 20. Man, goodness.
Christmas miracle. Okay.
Yeah, it was amazing. Okay, probability of a red in this one.
All right, so I did the baseball sum. I got 3 plus 9 divided by 7 plus 14. The combining,
12 over 21.
and it's 0.5714.
0.5714. Oops, let's zoom that one down a little bit. 0.5714. So which hat should we take? Which hat did you take? What was your hat?
I take the white hat.
You take the white hat. Now, how many find it weird that when we had the two tables separate and the hat separate, and each time you took the black hat, and we combined the balls, and now we take the white hat? Is that weird? It is kind of weird, right? And that is what is known as Simpsons paradox. Okay, and there's a definition of Simpsons paradox. We weren't sure how much time we'd have, so we said, well, we'll give them a very quick introduction with this simple example, and then point out that there's a fuller explanation of this on Wikipedia, and there's a couple of beautiful examples. And we actually would have time to look at a couple of the examples if I could actually connect to the internet.
Sure,
but you know how to connect to the internet.
yes, this is one of my
Well,
superpowers.
your computer knows how to connect to the internet.
So what I searched for is Simpsons TV show. That's what I searched for?
Something like that.
Okay.
Let's go on that. And let's just take a quick look at this. And the interesting thing is, it seems like a little weird probability quirk, but it has real life implications. And they go through some examples in here which are very cool.
So this little blue and red example, this is like the first hat. is like the second hat, and there's sort of a trend in one hat, a trend in the other hat, and they're both the same way. They were both, the black hat was better in both groups. Then you combine the groups and it reverses. And then all of a sudden in the combined groups, the white hat is better. So it's kind of a picture version of this.
And you mentioned
Two black hats is
you
worse
mentioned the baseball
yeah,
side. So the baseball example's in here.
Ooh. Hey, look, here they spelled correlation with a K. That's cool. Okay. Is the baseball example in here?
Baseball there. That's a very interesting example there.
Yes, this is the
That's
one.
a long one. That's a long one.
I remember when I was a student, they told me all about this, and they were very excited, and I was like, geez, who the hell cares? But let's go to a different example. Okay.
Kidney stone example. We'll go back to the kidney stone example. Let's
Okay.
go to the batting
averages.
Batting
Oh my God.
averages.
Here we go. Okay. The batting. Oh, because it really is the baseball sum. Oh my God.
It is the baseball sum.
All right. So these are baseball players. Derek Jeter. I know who Derek Jeter is because I lived in New York and I went to a baseball game and he was playing on the field. Isn't that amazing?
Were these people even playing before these or after these people were born?
I don't know. Yeah. Who knows? Who's heard
They're
of Derek
getting-
Jeter? All right. Yeah.
Hey,
Okay.
so-
There you go. All right.
But you got to be like, it's like hearing a Babe Ruth or something like that, right?
So Derek Jeter did worse than David Justice in 1995. You see, his batting average was only .25 instead of .253. So .253, slightly better. This guy, the real hero of the piece, David Justice, A+, we like him. And then in 1996, he did it again, that son of a gun. .321 is better than .314. So David Justice did better in 1995 and did better in 1996. Who did better when you combine the years? Derek Jeter. It flips. What? Better in 1995, better in 1996, but worse in the combined total of 1995 and 1996. This is very weird.
It's very weird. It's very weird. Now, let's go up to our kidney stone example. So the kidney stone example is a case where there's a real consequence of this, a real application here. So they've got two treatments for kidney stones, and the idea is these percentages are the percentage of successful surgeries. And if the stone size is small, let me tell you, kidney stones are horrendous. I have had them a couple times, and they are absolutely horrendous to get. But
now I see
nonetheless,
why you're so passionate about this example.
Exactly. It is, yeah. We can go on about that. Anyhow, when they use treatment A with small stones, they get a successful outcome, successful treatment 93% of the time. But if they do use treatment B, you get a successful treatment only 87% of the time. If you look at large stones, treatment A is successful 73% of the time, but treatment B is successful only 69% of the time. And yet when you combine the data for the small and large stones combined, notice that you've got 350 cases, 273 of them are successful, 78% are successful when they're combined for treatment A, but 83% are successful for treatment B. Looking at the combined data, it looks like the best treatment is actually treatment B. Now, where's the what's the explanation behind here? Well, the reality is treatment A is better for small stones and it is better for large stones, but there are a lot more small stones than there are large stones, and so with the small stones they tend to get lots of successful treatments. It's probably a less invasive treatment or something like this. They tend to do very well with that with treatment B. And you notice that they relatively rarely use treatment A on small stones. Large stones, though, are ones that they're much more focused on a successful outcome, and so If it's large stones, they notice that they're much more likely to use treatment A with the large stones. So that's where it brings in that kind of weird bias that when you get the combined groups, it's not telling the proper story of which is the best treatment. There's other examples in there. There's lots of stuff that goes beyond what we're doing in this course, but as you move into your future courses, you're going to see all kinds of other cool things about probability. There's so much nice stuff up on the web now on YouTube and Wikipedia, various other things, books, whatever, where you get to explore some of the great fun things about probability. I think probability is one of the most fun areas of both mathematics and statistics. It has been an absolute pleasure to have the opportunity to try to introduce you to more of this, and as you go on to your future courses, you're going to learn more, and what we would do is we'd say, wish you all the very best as you move up in further semesters.
I think in a probability course you're supposed to wish good luck.
Good luck, yes, but arrange it so good luck comes your way
Yeah, good.
by studying hard.